Okay, okay, now it's coming. Thank you. Okay, thank you. Good afternoon. So for the past few years, I have been working on a number of optimal segment problems. I'm going to explain what that means later. And because of that, I learned a pattern of algorithm which is usually used to deliver linear time solutions to a certain class of optimal segment problems. I think that pattern is very elegant. So I went to a colleague of mine doing algorithm and asked him, is there a name for this pattern of algorithm? He said, no, I wouldn't call that a pattern. And I said, oh, okay, how do you have a name for this technique? He said, I wouldn't even call that a technique. Because for those smart algorithm people, this is something so trivial and easy that it doesn't even deserve a name. But however, I think for us doing programming languages, it is our obligation to discover such patterns, even though they think so, and give it a name, a reason about them, and formalize them so that they get better known. So here it goes. So actually, the paper is actually about using that pattern to solve optimal partitioning problems. But however, the cases for segment problem is much easier, so I'm going to talk about that first. So what is a segment problem? So given is a list of elements of a certain type E, and what we do is the specification is to compute all segments of it. By segment, I mean a contiguous sublist of the given list, which can be computed by computing all the suffixes of the list before taking all prefixes of it. And here, this inits and tails are the standard Haskell functions, which respectively gives you all the prefixes and the suffixes of the list. And from all the segments, I want to choose, and I want to pick some optimal ones. Which, by being optimal, I mean the ones that minimize a certain cost function W. Okay, that's the specification. And what follows are merely standard calculation. We start from the specification and expand the definitions. And now we distribute min by W into concat, which gives us this. Min by W after inits. That's given a list, compute an optimal prefix with respect to the cost function W. So from here we learn that the computation of optimal segment can be carried out by computing the computing optimal prefixes for each suffix. And so I'm going to give you the name that min by W after init is to be called optpref for optimal prefix. So the computation may be carried out something this way. So now this blue part is one optimal prefix of the list of elements processed so far. So every time in every step you read in one new element and compute its optimal prefix, and reading another element and compute its optimal prefix, and so on. And then the best one among those blue ones is your optimal segment. Okay, so now if each of these optimal prefix does not extend further right than the previous one, which means that the computation of optimal prefixes can be carried out in a fold R. Then we can do something like this. So okay, now here is optimal pref, and if the newer prefix does not is never longer than the previous one, okay, then oppref can be turned into a fold R. And what could this algebra be? Okay, as anyone? Okay, as a specification, it can be as simple as, say, simply attaching the new element to the left end by a cons and just compute an optimal prefix. Okay, and this is going to be simplified later. But then there's this well-known fold lemma saying that map of fold after tails is a scan, meaning that computing optimal segment can be carried out by one pass over the input list. Okay, that's good. But that does not give us a linear time algorithm immediately. Okay, to now, okay, we can to compute the optimal segment. We can do we can just look through the input list once, and in every step we do this. But however, to have a linear time algorithm, is we have to somehow make this run in constant time, which does not look easy in general. Okay, it's possible for maximum segment sum problem, but not that easy in general. So what do we do now? So the goal now is to try to simplify this. And the main idea is that, okay, in each step, how many prefixes do you have to consider? Each time you're reading one more element, there's a linear number of prefixes which could be the optimal prefix. So the idea is, if it is possible to somehow reduce the number of prefixes you have to consider by throwing away those points, which will not possibly be the right end of any optimal prefix, whatever this new element is, and keeping only those ones which could still be could still possibly be useful, then it might help to speed up this a bit, to speed up this a bit. Okay, then, so what property do we need to throw away some unnecessary right ends? Okay, so then for this algorithm, this is what we wish to have. So the cost function we are considering is W, but we assume the existence of another auxiliary function called delta, and together we wish that they have this property. So if the delta for two lists x's and y's, if the delta value of x's is no bigger than that of y's, then this happens for any ws. Okay, among these three, either this one is better than ws append x's, or ws append x's append y's is going to have a smaller, better w value than ws cons x's. So we don't know which one, but anyway, one of these is better than this. So when that happens, so this one can be thrown away, and we need to keep only two of them. So that's why we call this property 2 in 3. And also when that happens, this x's and y's can be seen as one atomic block. So it's either kept together or thrown away together. Okay. So, okay, if we have this property, then this is one thing we can do. So now, okay, that's the same property written formally. Okay, then now, if we have that property, we can now organize the currently optimal prefix as a list of blocks in strictly decreasing delta value. Now, so this is the previous optimal prefix, already split into blocks in decreasing delta. Now, each time we read in one more element from the left, we examine the delta value of this one and this one. And if this one is no bigger than this one, that means these two can be seen as one atomic block. So they can be glued together into one block. Okay, now again, compare the delta value of this one and this one. Again, this is smaller. So these two can be glued together into this. So we keep gluing blocks from the left until the decreasing of delta value is restored. So that's what we do each time when reading one more element. Okay, then another property that we wish to have is this. Assuming that this is a list of atomic blocks. Assuming that the delta value is sorted decreasingly, then to find out an optimal prefix, we wish that we can start looking from the right, and then compare to adjacent blocks. Okay, so the blue ones are the W values, and the orange ones are the delta values. So if the W value for the optimal prefix, for the prefix ending here, is smaller, is no, is bigger than the W value of the prefix ending here. Okay, remembering that we are looking for smaller the W values. So, okay, so now this one is a better prefix, a better right end of the prefix. So let's carry on, and then we look at the next two blocks. Okay, so the W value of this of the one ending here is better than the one ending here. Okay, good. We keep looking from the right, and now okay, we see for the next block the W value is bigger than this one. Then we can just stop and declare this one to be the optimal prefix, because the W values of the sequence is going to be like this. So this is always descending and then ascending. So we can start looking from the right and try to find the lowest point, and without having to look further. So what does that give us? So okay, this is what happens. This is how the entire algorithm basically looks like. So we organize the currently optimal prefix in a queue of blocks with descending delta value. And each time we retain one more element, we perform some joining here on the left, and to restore the decreasing delta values, and throw away some elements from the right to find out the best optimal prefix. And that's one big step. So now we have the best prefix for this suffix. And then retain another element, do some joining here, do some training on the other end. That's the next big step, and so on. So then eventually the best one among the orange ones is the best segment. Okay, so, and what about complexity, right? So observe that each block can be joined, can be glued with the block to its left at most once. Okay, and so this gluing could happen at most a linear number of times throughout the entire computation. And similarly, each block can be thrown away at most once. So this trimming could happen at most a linear number of times. So that's why it's important that we don't have to examine the middle of the queue. So overall, we have a linear time algorithm because each of these operations runs in amortized constant time. So I think this pattern is quite elegant. So that's why I wanted to formalize it. And so eventually the name queuing and gluing is suggested by Jeremy Gibbons. Thank you very much. Right. Okay, but however, it looks nice, but for this to work, we want the cost function W to be 2 in 3 and also bitonic, which seems to be asking a lot. So are there many functions satisfying this? Okay, actually, the simplest function I can think of, which actually satisfies both property, apart from that, with the direction of inequality is reversed, is the average function. By average, it's simply the sum of the list divided by the length. Okay, this function happens to satisfy both property, but however, the average function has some other annoying properties which makes the computation of the maximum average segment a very, very difficult problem on which I spent 4 years and want to forget about it afterwards. So, and then the problem that we're doing now is much easier, much nicer, not easier. Okay, and then for other problems, actually, smart algorithm people develop another scheme to construct the delta function given W. So they have this theorem saying that if there exists given W, if there exists delta and K satisfying this equivalence, then W will be 2 in 3 with respect to this delta, and Then there are some property about K which I need to omit from this slide. And so how do you construct this delta? Basically, you start from the left-hand side, write this down, and then try to shunt everything mentioning x's append y's to the right-hand side, and keep only y's on the left-hand side of the inequality. Then if you can do that, this will be the delta function you want. And this will be the delta function that will work. Okay. So, and actually the same property also guarantee the bitonic property. Right. So far all these were our hands waving, and the actual derivation I enjoy doing, but I'm not sure you want to see that. So what I want to mention is merely that at one point I find it much easier if I use a relation which models joining two adjacent blocks, joining two arbitrarily blocks that are adjacent. And then the most interesting step of the derivation is a fold fusion, which fuses this relation glue, the reflexive transitive closure of the relation glue into the fold R, and then do some simplification inside, and that's going to give an algorithm we saw in diagrams just now. Okay, so that was about the optimal segment problem. But however, what we actually solved in the paper was optimal partitioning. So optimal partition. The problem is that given a list of elements, we want to find out the best partition with respect to some cost function. So for example, now given a list 1, 2, 3, its partitions include 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay, so among them, we want to find an optimal one with respect to some cost function on partitions of lists. Okay, then the problem gets more complicated, but however, it can be solved with the same principle. And it turns out that optimal partition problem can be solved by solving a sequence of by repeatedly solving optimal prefix problem, provided that you use a special cost function, in which being optimal means being the best prefix for the best first segment of the partition. Okay, how do we do that? Now, the function of the parts made look like this. For empty lists, you give an empty list, and for other lists, okay, the optimal partition is y's optimal partition of z's, where y's is an optimal prefix with respect to some cost function w, and z is the rest of the list, by chopping y's away. And what's this cost function w? It's this. Okay, the w of y's is this cost function w cost h, assuming that the rest of the list is optimally partitioned already. And you see this suspicious circular dependency. And does that work? Actually, this works if you store all the optimal partitions of every tail in an array, and carefully compute them one by one, starting from the shorter ones to the longer ones. Then this is going to work, amazingly. And so yes, so then the actual this is still quite abstract, but if the definition of the partition is something like this, in which it refers to the array store containing those optimal partitions. So these are mutually recursive. Okay. So what problems have we solved with this? So in the paper we gave several examples. There is a scheduling problem from the previous work of Brooker from the algorithm community, and also a smart student of mine noticed that actually the algorithm can be applied to solve paragraph formatting problem. The goal is to partition a given list of the partition a given text into lines, so to minimize the sum of square of this white space in the end of each line. And then it turns out that if we write down the cost function is like H is sum of map of W, and W is the amount of white space in the end of each line squared. And then somehow, if we write down this, so this is similar to the previous equation, but slightly complicated because the detail of the list Z needs to be taken into consideration. But the principle is similar. You write down the left hand of the equivalence, and then somehow shuffle everything around. And after several steps of computation, you reach this. So now this part, this complex-looking part, is the function, is the delta function. And to tell the truth, I have no intuition why this works. But somehow, well, it just worked because it was proved. Okay? And so that's all I have to say today. So in conclusion, we have formalized an algorithm pattern, which we call queuing and gluing, which I think is quite elegant. And we use that to solve several, several complex problems. And that's it.
Other questions? Here in the front.
Hello, I'm Matthias Goergens. Can you give some more examples of what kind of problems you can solve with this?
Sorry?
Can you give some more examples of what kind of problems you can solve with this approach?
Okay, the examples I know of so far are this text formatting problem and a scheduling problem proposed by Brooker. It's about so you have a list of jobs which you want to divide into batches, and the finishing time of each job is the finishing time of each batch. And then for the job lady, then the cost function is something like the sum of the finishing time of all the batch, something like that. And then somehow that problem can also be solved by this scheme. And also the delta function is also discovered using the same property. And that's about actually that's about the only problem I know of.
Okay, next question.
Hi, Ken-Shan. I'm not sure if the paragraph formatting algorithm in tech is linear time. It's obviously not quite computing the same thing as you are because it evaluates paragraph goodness differently. But I'm just wondering if you know of a comparison between what you concluded with and what tech does.
Okay, I'm not sure the problem in text is the same as this one, but yeah. But however, this formulation of this version of paragraph formatting problem does already have a linear time solution, simpler than this one. So this is just one example where it surprisingly works, but it does. I'm not claiming that it's a better algorithm. And for other text formatting problems, actually, I don't know.
Okay, we have one more question in the back.
Hi, Jeremy Gibbons from Oxford. Can you put your finger on quite why the average function is so bad and caused you so much pain?
Okay, the average function satisfies both properties I need, but then the problem is that it is not the prefix close, suffix close, meaning that actually the first thing I want does not hold. That if the cost function is average, actually computation of the optimal prefix is not a fold R, because because the optimal prefix could extend further than this. Okay, now assuming that this is an optimal prefix, and here you're reading one more element, which is a very, very negative value, for example, and now so this is going to pull down the average a lot, and then to undo the damage is preferable to extend this much further, to distribute the negative value to more elements. So actually, ultimately, the average function is if the cost function is average, the optimal prefix is not a fold R. But then the funny part is that it doesn't matter. So in existing algorithms for optimal, for the maximum average segment problem, we could somehow we could just pretend that it doesn't happen and carry out the computation as a fold anyway. And then the difficult part would be proving that this is still correct. And that's what we spent 4 years on. And
Okay,
so
thank you
for
very
asking.
much. Thank you. So in the last presentation of this